All right, so continuing our discussion of kind of the building blocks of circuitry, today, or in this video, I want to discuss Ohm's Law, and as with dielectrics and with current, there's sort of a macroscopic and a microscopic view on what is Ohm's Law. So the last two times I started with the macroscopic point of view. This time I'm going to actually start with the microscopic kind of point of view. All right, so this is an example of something, here's a Jeopardy word for you. It's called phenomenological. Phenomenological law. So what that means is it's not something which is guaranteed to always be true. It's something that kind of comes out of experience and experiment. And many times these kind of relationships start as empirically derived from experiment, and then maybe later on they can be proven from more fundamental theoretical reasoning, or maybe they can't always be proven, but in special cases you can verify that the fundamental theory is at least compatible with them. So anyways, phenomenological rules or phenomenological law. All right, so Ohm's law is one such example of this. And the idea goes as follows. Imagine you have a wire and we hook it up to a battery or something. Okay, so you hook it up to a battery and the battery, or the effect of hooking up to a battery, generates an electric field. And then because there are charged particles, charge carriers that are moving, we start to get a drift velocity, as we discussed last time in our discussion of current. Okay, so the idea is the battery creates an electric field which causes charge carriers to move. Now, we discussed last time that the flow of charge carriers, they bounce off each other, and they bounce off the structure of the wire. It's not just a free flow. It's more like a friction or drag, or some sort of a flow with resistance. And in fact, experience says that it reaches a terminal velocity. So the charge carriers don't just keep accelerating forever. They eventually reach a terminal velocity called the drift velocity. Okay? And that led to the concept of a current density. So current density was the current per unit area which passed through a wire. So, all right. So let's kind of focus in on a little spot here. So imagine you made a little loop right in there. It could be an infinitesimal, teeny tiny little loop. And we want to think about, okay, what could the relationship be between the electric field, which we know causes the flow, and the actual amount of current per unit area going through that area? So basically, and so you have to think about it. The electric field is defined everywhere throughout the wire. So that means the electric field is locally defined. And so we should be looking for a relationship between the locally defined electric field and whatever local variable would describe current flow, namely the current density. The current gives you the overall amount of flow through the whole wire, but the current density is the amount that would pass through this little patch that I put with a small circle. So here it is. Here's the phenomenological, here's Ohm's Law. And what it says is, the basic idea is, oh, well, I expect that if I increase the electric field, I'm going to get more flow. So we guess that the current density, J, equals some constant, sigma, times the electric field. Sigma is called the conductivity. So it measures how easy it is to get a flow. So basically, if you have a large conductivity, then even with a small electric field, you can get a significant current density. So you can get significant flow. So the bigger sigma is, the easier it is to make things flow. In fact, yeah. So you can, conversely, if sigma is small, then it takes a larger and larger electric field to push the current through. Okay? So that's the concept of conductivity. Large sigma means it conducts very easily. The units on sigma, if we're going through it, remember J would have units of current per unit area, so that's going to be amps per meter squared, and the electric field is, well, we could think about that as a volt per, electric field would be a volt per meter. So I could think about that as let's think about that. So that would be, I think if I'm doing that right, that's going to be an amp. The units of it would be an amp per volt meter, I think. I've got that right. Let's think about that. Let's just work it out, all right, rather than guess. This is going to be, J is going to be amp per meter squared, current per unit area, is sigma, and this should be a volt per meter because the derivative of the potential gives you the electric field. So sigma should be an amp per voltmeter. Yep, that works. That's good. Okay, so that is those are the units on conductivity. Now, so if you want to measure how easy it is for something to flow, we talk about conductivity. On the other hand, in other contexts, rather than focusing on how easy it is for things to flow, we're more pessimistic and we think about how hard it is to get things to flow. So we can define resistivity and, let's see, what symbol was I using for that? Yeah. Rho, yeah. So I can define resistivity to simply be rho, not charge density, not any other sort of density. It's resistivity is just defined to be 1 over sigma. I think that's just the standard definition. So the units of resistivity would be the opposite of what I had before. So that would be a volt times a meter divided by an amp. And what this would say is, if you have a very conductive thing, so if the conductivity is large, then the resistivity is small, and vice versa. If the conductivity is small, the resistivity is large. So you can turn this around and we can say that the electric field equals the resistivity times J. All right, so we have conductivity, resistivity, current density, and electric field. These are all microscopic, intrinsic properties, things that live, data or information which lives inside the wire, like at a little point inside the wire. These are the local pieces of information, okay? So these are properties, specifically sigma and rho, the conductivity and resistivity. Those are characteristic numbers which characterize the different materials at different temperatures. So if you know the temperature and the type of material, you can look these numbers up from various chemical data books and property tables. There would be a different resistivity for copper versus iron versus lead versus, I don't know, wood. So, okay. And I expect things which conduct very well to have a large conductivity and therefore a small resistivity, and things which are not good conductors, I would expect to have small conductivities and large resistivities. Okay? These are phenomenological rules. There's no kind of deep principle which says this has to happen. This is something which is observed to happen in many different materials. It's phenomenological. All right, so that's the microscopic perspective on Ohm's law. Next up, I'm going to derive from this the macroscopic view. So what I want to do is go back. I probably should have kept my picture. I've got my wire here with the electric field. And let's go ahead and say that the wire has a length L. And I can relate the electric field on the inside to the change in voltage from either end. And what I get is delta V up to a minus. I'm not worried about the minus sign right now. So should be, we assume that in the wire, the electric field is more or less constant. So I can say that's E times L. I should have said something earlier. I would have given you a hard time for not stopping me, but I can see that's hard for you right now. Wait a minute. I have an electric field inside the wire? How is that possible? Remember, I thought there were supposed to be no electric fields in the wire. Well, we aren't, because we're hooking this up to a battery, we're never letting it reach steady state. We keep pumping more and more charge in. So we keep the system, we drive the system, so there's going to be an electric field acting across it. Okay, so that's why it's different than other examples that we had before with a conductor where you just put the charge in, wait a second, let it rearrange, and then it reaches equilibrium and there's no charge or no electric field in the inside. Well, here we're never letting it settle down. We keep pushing more and more charge in. I should have said that before. Okay, so rather than talking about the locally defined electric field, we can talk about the potential difference between either end. Similarly, rather than talking about the current density J, I could multiply by the cross-sectional area A, as long as we assume that J is constant, and that should give me the current through the loop. So my equation, which said that the electric field equals the resistivity times J, that equation can become delta V over L equals rho times J, which is the current, divided by the area. And if I rearrange this equation, I can say that delta V across this material equals L times rho over A times I. This combination is given a name. This combination is called the resistance. Rho is the resistivity, R is the resistance of the wire or material. So I'll rewrite that up here. We have a microscopic equation which says that the electric field is equal to the resistivity times the current density. And we have the macroscopic bird's eye view, or what you see when you sit at a table and you measure things, which says that the voltage drop equals the resistance times the current, V equals IR. And where the resistance is rho times L over A. The units on resistance are that we give them the name ohms. They're called ohms. So this is Ohm's law written microscopically. The macroscopic, the tabletop perspective. This is Ohm's law, and they're connected through all the formulas we've seen. The unit you have on the resistance is called an ohm. How do you think about this? Well, okay, so you imagine you have some material, I don't know, iron. Okay, it has some intrinsic resistance, we call it resistivity, to current flow, some natural amount of friction, I guess, that's baked in the cake. Okay, so that controls it to some degree. On the other hand, if you had a long wire, then all of the little bits of friction kind of accumulate, and it gets harder and harder and harder to push the current through. So the resistance grows with the length of the wire. On the other hand, if you make the wire very thick, have a large area, then it's like you have more and more parallel paths. So actually, the larger the area, the easier it is for the current to flow, so the smaller the resistance. Another way to think of it is as like traffic, car traffic. If you are on a single lane highway, a single lane road, and you have to drive for miles and miles and miles and miles and miles, your odds of getting blocked at some point grow. So the longer the road, the more likely it is that you get stopped or slowed down. On the other hand, if it was a 10-lane highway, well, then you're much less likely to get blocked by something because you can you can wander around. Okay, so there are more parallel paths. That's analogous to increasing the area, and that lowers the resistance. So those are good ways to think of it. Okay, so that's Ohm's law, and it relates the voltage applied across something to the current flow through something. It's a phenomenological law. There's no guarantee that every object or thing obeys this, although many, many, many things do, and even things which don't always behave like this, sometimes within a limited range of variability, like if you don't change the parameters too much, it's a good approximation. Materials which obey this law, usually it's written as V equals IR. Things which obey this law are called ohmic materials. Ohmic materials. Okay, so some things are ohmic and some things are non-ohmic. Examples of things which are ohmic are resistors. So if you ever see a picture of a little resistor, that's definitely something which is ohmic. Something which is not ohmic, excuse me, might be a diode or a transistor. There are lots of things which are not ohmic, but for many materials, as long as you don't crank up the current too much, you just look at small, inputs, small voltages, small currents, then you can approximately use this rule. All right, so that's Ohm's law. Next up, we're going to talk about, let me think here. All right, so next up, we're going to talk about a little bit about batteries and EMFs. And at that point, we can actually try to do something. We've got resistors, we've got capacitors, we'll have batteries and wires. We can pull it all together and build circuits. All right, see you next time.